Hi everyone, welcome to the second of 3 videos going through some past exam questions on electrode potentials. The first question here is one that's exactly the same as in the first video. I want to show you that these kind of questions come up regularly. It's exactly the same. It's a 2-mark question. What's the standard electrode potential? Include the standard conditions. Okay, so this is a question that we definitely want to be prepared for because we've seen it comes up multiple times. So the standard electrode potential is the EMF. Okay, remember that stands for the electromotive force, so it's telling you what is the force that's making the electrons move, of a half cell compared to the standard hydrogen electrode. We can use the terms half cell and electrode interchangeably, essentially. And then including the standard conditions, so it's 298 Kelvin, it's 100 atmosphere, no it's not, it's 100 kilopascals, or 1 atmosphere, and then solutions 1 mole per decimeter cubed for their concentration. Okay. And so that's hopefully a fairly straightforward one. Part B here is a bit less straightforward. This is one that's definitely worth thinking about. So this is showing you, again, 2 redox systems, looks fair enough. Copper half cell and a silver half cell. We've got their electrode potentials, measured the cell potential. We'll talk about this in a minute. Write down the equation for the overall cell reaction. This is straightforward. So what's happening here then, out of the 2, the silver half cell is the one that's got the more positive value. And remember, the key to all of these questions about electrode potentials, the more positive value is the one that's being reduced. Okay, so therefore this equilibrium is going from left to right and the copper equilibrium is going from right to left. So therefore our reaction is going to involve Ag plus reacting with copper, and it's going to give us the products of Cu2 plus and solid silver. Okay, but remember, if we add these 2 equations together, we need to make sure the electrons balance. So this half equation here would have to be multiplied by 2. So we need a 2 here and we need a 2 there. And you should find that that then makes the charges balance. There's 2 plus charge here and a 2 plus charge on that side. Okay. Now this second part is a bit that's interesting then. It then says water is added to the copper half cell. This changes the position of equilibrium and the cell potential increases. Now we need to be really careful here that this is talking about the cell potential, not the electrode potential. Okay, that is a different thing. These are the electrode potentials for each of these electrodes. The cell potential, remember, is the difference between the 2. So the cell potential, the difference between the 2 is increasing. It doesn't mean that this 0.34 value is increasing. You've got to be really careful with that. So explain in terms of equilibrium why the cell potential increases then. Okay, so what difference is this going to make? If we've added water, well, water's not involved here anyway. There's no water in the equation. But if I'm adding water, then what am I doing? I'm just diluting it, right? I'm just reducing the concentration. So I'm going to reduce the concentration of the aqueous copper ions. Okay, it's not going to affect the solid copper, is it? But it's going to reduce the concentration of Cu2 plus. That's the first thing we can write. So adding water reduces the concentration. Now let's just write it like this. Concentration of copper 2 plus. Okay. So if we've reduced the concentration of this, then this equilibrium is going to shift to the left, isn't it? Okay. To try and increase the concentration again. Okay, it's Le Chatelier's principle. So adding water reduces the concentration of Cu2 plus. So the equilibrium shifts to the left. So that means then that more copper is going to be oxidized and lose electrons. Okay, so more copper solid is oxidized. And therefore we said, didn't we, the golden rule of all this electrode potentials thing is the more positive the value is, the more it's being reduced. So if this is now being more oxidized, this value is going to become less positive. And this is where we have to be careful, because it's not saying that the electrode potential gets bigger. Actually, this electrode potential is going to get smaller, or it's going to get more negative, or less positive. Okay, so more copper is oxidized, so the electrode potential decreases. That's why it's important that we understand the difference between the electrode potential and the cell potential. If that electrode potential decreases, then the cell potential, which is the difference between the two, is going to increase. There's going to be a bigger difference between the two if that gets smaller. Okay, so that's why the cell potential is going to increase. Okay. This means there is a bigger difference between the electrode potentials. So the cell potential increases. So it's quite subtle, that one. You need to be super accurate with what you're saying. Okay. And try and make sure we've mentioned everything here. So it does say in terms of equilibrium. So we did talk about the equilibrium. We talked about the values of the electrode potentials, and then we talked about the value of the cell potential. So I think we've covered everything we need to put there. Okay. The next question we've got, again, gives us some equations here. So this says, this is another question where we need to look very carefully at what it says. Okay, so we've got an aluminium oxygen cell. Now, it says the reactions at each electrode are shown below. And I don't know if you can pick this up on the video, but reactions is written in bold here. Okay, so they're trying to flag that up for some reason. Okay, and if we look at these equations, these are not written as equilibria, right? The last question we had, here's the equilibria. What we're saying is this is not an equilibrium. This is the actual reaction that's happening. We've made a decision about which way the equilibrium is going. Okay, it's not going, oh, it's an equilibrium. No, this reaction's happening and that reaction's happening. Okay, that's the way they're going. So that's an important bit of information for later on. So the standard electrode potential for the oxygen is plus 0.4 and the cell potential is 2.71. What is the standard electrode potential of the aluminium one? Okay, well, that's fine. So the cell potential is the difference between the two, isn't it? But we need to be careful because there's actually two possibilities here. Okay, we need to do the difference between the two electrode potentials. Okay, so it could be that this electrode potential is 3.11 and then we take away 0.4 to get 2.71. Or it could be that we're doing 0.4 minus 2.31 to get 2.71. Okay, both of those would work. It depends on whether this is the positive value, the more positive value, or whether this is the more negative value. How are we supposed to know which one of these is correct? Well, this is where the key is, that these are the reactions that are happening. This reaction is being oxidized, look, because it's losing electrons. This one is being reduced, so it's gaining electrons. Okay, and then remember the golden rule. If it's being reduced, that's because it's the more positive value. This one must be the more negative value. So in other words, the oxygen's 0.4 is the more positive value. So therefore, this is the correct one. This is not correct. Okay. So the electrode potential for this one must be minus 2.31. Is that okay? And then construct the overall cell equation. So now we just need to add these two reactions together. But to get this to work, then we need the electrons to cancel each other out. So what we're going to have to do is we're going to have to times this one by 4 to get 12 electrons, and we're going to have to times this one by 3 and then add them together. So we're going to have 4Al plus 16OH minus plus 3O2 plus 6H2O goes to 12OH minus plus 4 aluminium hydroxide. And the electrons will cancel out, won't they? So we get to here, and then we can see we can cancel out some of these hydroxide ions, right? And you should always do this. If you can cancel something out, you should. So we'll cancel those 12, and we'll change that to a 4. And then let's just write this out again. So it's neat. 4Al plus 4OH minus plus 3O2 plus 6H2O reacts to make 4AlOH 4 minus. Let's just check everything's balanced as well. So we've got 4 aluminiums and 4 aluminiums. We've got 4 OH minus ions. Okay, this is going to be awkward. So 4 oxygens. Let's just do this. That's 4. 3 2s is 6, and another 6. So we've got 16 oxygens here. 4 times 4 is 16, so that's good. Hydrogens, we've got 4 there and 12 there. And again, we've got 16 hydrogens, so 16 and 16, that's fine. And 4 minus and 4 minus for the charge. So we can be pretty confident we've got that right. Okay, carrying on. Here's another question, looks a bit similar. We've got a table full of equilibria and electrode potentials again. So, as I said, these questions do kind of repeat after a while. They do start to look a bit similar. We've got a question here that's very similar to one that we've seen in the previous video, if you watched the first one. We've set up a cell here, and it wants us to draw a labeled diagram to show how to set it up. Okay, so we've seen this before. And again, make no apologies for going over the same questions, just to give you the point of, look, this comes up. You need to make sure you can do a question that asks you to draw a cell. Okay, so make sure you've practiced this and make sure you're comfortable with it. We're going to have 2 beakers, we're going to have 2 electrodes, they're going to have solutions in, they're going to be connected by a voltmeter, we're going to have a salt bridge so that ions can move and prevent charge from building up. Okay. And then we'll say a labeled diagram to show how they could have set up cell A, which is based on redox systems 1 and 2. Okay, so redox system 1 is nickel 2 plus and nickel as a solid. So we'll have a solid nickel electrode, and we'll have a solution of nickel 2 plus aqueous. And number 2 is Fe3 plus and Fe2 plus. And can you see again, if you've seen on the previous video, this question's come up 3 times now, and every time there's been one half cell which has involved 1 solution and 1 solid, and the other half cell has involved 2 different ions in the solution. So this is Fe3 plus and Fe2 plus, and therefore we have to have a platinum electrode, right? So they really like testing that you know what to do if you've got 2 different ions in the solution. Okay, it's 3 marks here, and we get 1 mark for having the electrodes, the voltmeter, and the salt bridge, and then 1 mark for each of your half cells. And again, we perhaps should be careful. It does say to measure the standard cell potential, so we should really put the standard conditions on. We don't need to write about the temperature and the pressure, but we should say that this is going to have to be 1 mole per decimeter cubed solution of nickel, and it's going to have to be 1 mole per decimeter cubed of each of these, because it's the standard one, so we should really put that on. Okay, it then says for each standard cell below, what would be the standard cell potential and what would be the sign of the nickel electrode? Okay, so let's have a look back at here. So cell A, which is based on system 1 and 2, so that's the one we've just written. The standard cell potential then would be the positive one, take away the negative one. So it's going to be 0.77 minus 0.25. So that is going to be 1.02. And what's the sign of the nickel electrode? Well, out of those 2, it's definitely the negative one. And it is genuinely that simple. It's the negative one out of the 2. Okay. And then cell B is based on redox system 1 and 3. So here, 1 and 3. So you see this time, actually, the minus 0.25 is the more positive one. Okay. So we're going to do minus 0.25 minus 0.74. So we get 0.49. And then what's the sign of the nickel electrode going to be? Well, actually, out of these two, out of 1 and 3, this is the positive one. Okay, even though it's actually negative, relatively speaking, it's the positive one out of the two. Okay, so it's 0.49 and it's positive in that case. Right, this question then continues, and it says the student left each cell in A, so the two cells that we just talked about, connected for a length of time. For each cell, the student weighed the nickel electrode before connecting the cell and after the cell had been disconnected. They made the following observations. In cell A, the nickel electrode lost mass. In cell B, the nickel electrode gained mass. In both cells, the measured cell potential slowly changed. Explain these observations and include equations. Okay, so basically this is asking us to write the overall cell equation for each of these cells. Okay, let's do that first, then we'll worry about what this is going on about in a minute. If it says write the equations, let's just write the equations. Okay, so cell A was the one that was based on redox systems 1 and 2. So if we combine these two together, we're going to have to multiply this second equation by 2. And the second equation is the positive one, so it's the one that's going to be going left to right, being reduced, and the nickel's going to go backwards. So it's going to start with 2 Fe3 plus reacting with nickel. Okay. And I'm going to put the state symbols on. It doesn't mention the state symbols here, but I'm going to write them on because it will help us illustrate what's going on here. So it was 2 Fe3 plus reacting with solid nickel, and therefore it's going to end up making nickel 2 plus aqueous and 2 Fe2 plus aqueous. Because again, we multiplied this by 2, didn't we, to get the electrons to balance. So nickel 2 plus aqueous and 2 Fe2 plus. Let's just check the charge is balanced to make sure we've got that right. So we've got 6 plus charge here, 2 plus and 2 lots of 2 plus. So yeah, 6 plus and 6 plus on each side. Right, if we now look at this, and again, if we look at the state symbols, we can understand why in cell A the nickel electrode is losing mass, right? Because solid nickel is being converted to nickel ions in the solution. Okay, so solid nickel goes to aqueous. Oh God, I can't spell aqueous ions. So mass of nickel electrode decreases. I'm trying to fit this in the gap here. Okay, that's cell A. In cell B, we're assuming it's going to be the opposite way around, right? So I'm expecting to end up with an equation that has aqueous nickel ending up with solid nickel, and therefore the electrode will have gained mass. Okay. So let's have a look at that. This was redox systems 1 and 3. So it's our nickel one and the chromium. And yeah, in this case, this is going to be the more positive one out of the two. So this is going to react from left to right and make solid nickel so that the electrode will increase in mass. And if I combine these together, I'm going to have to times this by 3 and this by 2. So I'm going to start with 3 nickel 2 plus reacting with 2 Cr. Okay. So 3 nickel 2 plus aqueous plus 2 Cr as a solid. And that is going to give me 2 Cr3 plus aqueous and 3 nickel solid. Okay. And again, we've got 6 plus charge and a 6 plus charge, so that's balanced out. And here we've got aqueous, we've got the opposite of what we had above, haven't we? Aqueous nickel ions are forming solid nickel. So the mass of the nickel electrode increases. And then the final thing it says is that in both cells, the cell potential slowly changed. So why would that be the case? Well, if we're trying to measure this standard cell potential, It's only going to be the standard cell potential if it's under standard conditions. Okay. Why would it not be under standard conditions? Well, why is the temperature going to change? The pressure is going to change. There's no reason why that should change. What is going to change is the concentrations of the ions, isn't it? We've just said here the concentration of nickel ions would increase, and here the concentration of nickel ions would decrease. So therefore, they're not going to be the standard 1 mole per decimeter cubed anymore. So therefore, the cell potential is going to change. Okay. The concentration of nickel ions changes, so the cell potential changes. Because the concentrations are not the standard concentration, let's say. Okay. I think I might have written more than we really need to write there, but we should be pretty confident of getting the marks there with all that information. Right, the final one, just a 1 mark question here where we've got to work out a half equation. What's it saying? Nickel metal hydride cells being developed for use in cars. An alloy is used to absorb hydrogen. Right, fine. The overall cell reaction is shown below. The half equation at one of the electrodes is here. Deduce the other half equation at the other electrode. Okay, so these kind of questions, if you watch the videos on redox reactions, you might have seen a question like this before, where usually, all the way through what we've been doing, even in this video, is saying we've got 2 half equations that we need to combine together to give 1 overall equation, and we add the 2 together. Here, we've already got the overall reaction, so this must be the sum of this half equation and the other one. Adding the 2 together must give me that. So what I can do is do this overall equation minus this half equation, and that will give me the other one. And it'll look a bit odd, but go with me, it does work. So if we subtract this here, we're going to get MH minus, well, there's no MH in the half equations there, so MH is still going to be in it. The nickel oxide hydroxide is here, and then we're going to take away it from there, so that will cancel out. And I've got nothing else in the reactants here, but I'm going to have to take away H2O and take away an electron. And clearly this equation can't have minus things in it, but bear with me, we'll sort that out in a second. Then we've got the arrow. Then we've got metal M, take away nothing, so that's still going to be in it. Nickel hydroxide, take away nickel hydroxide, so that'll cancel out. And then there's nothing else here, but we need to take away OH minus. Now we can't have this equation with minuses in it, that doesn't make any sense. So all we need to do is anything that's got a minus in it, we just need to put it on the other side of the equation. Okay, so we can have MH plus OH minus reacts to make M plus H2O plus an electron. Okay, that's going to be our answer. I'll write it here on the answer line. So it's a bit of an odd method that, taking it away and you end up with these weird looking minuses, but then if you just shift it all to the other side of the equation, we can check this is right now, because if we've done this right, adding these 2 half equations together should give us that equation. So if I add these 2 together, I'm going to get MH plus that thing. The H2O is on both sides, right? So that's going to cancel out. The OH minus is on both sides, so that's going to cancel out. The electron's going to cancel out. And I'm going to get the metal and the nickel hydroxide on that side. Okay. So it's a slightly odd method of working it out there, but it does work.